Welcome to Lecture 34, 9.2, Estimating a Population Mean. Alright, so first off, here's a question. What is the goal of statistical inference? Well, remember, the goal is to use information, so let me go ahead and write this out. To use information obtained from a sample and generalize to a population. Okay, so we'll take a sample, make a sort of a statement, and then generalize it to the population. That's the goal of statistical inference. Alright, example 1. Given the following random sample data values, obtain a point estimate of the population mean. Alright, so this is just a random sample from the population. We're going to go ahead and find the mean. Well, the sample mean, what we're going to do, actually let me go ahead and rewrite this on the side so I can write it all out. You add up all the values and divide by the total, right? So that's going to be 24 plus 28.9 plus 27.6 plus 23.1. I'll go ahead and write them all out. Check back in with me in a second. Alright, so I went ahead and wrote down the rest of the items, and then we divide by 12 because there's a total of 12. Let's go ahead and stick this in our calculator and see what we get x equals. Alright, and we find that x bar, or the mean, is approximately 27.28. So that is the point estimate. Point estimate of the mean of the sample. Alright, so let's take a look at objective 2, stating the properties of the student's t-distribution. Alright, so first off, recall that different random samples would attain different random point estimates. Okay? So we want to construct a confidence interval for the population mean this time. And our confidence interval would be the point estimate value plus the margin of error. So what is the point estimate and what is the margin of error? So the point estimate is our x bar, and then our margin of error, so plus or minus. Margin of error is z, alpha divided by 2, times standard deviation divided by our sample size. But there's a problem with this. We need to know the population standard deviation sigma to find this. And it doesn't seem likely that we would know the population standard deviation and not the sample standard deviation. Okay, so that is a slight problem. We would need population, but we don't even know the sample. So trying to substitute the sample standard deviation would lead to problems because, remember, our sample standard deviation S will vary from sample to sample, so we can't just swap it in if we don't know what the population standard deviation is. Alright, so note, the Z-score we have right here, and notice for the Z-score we use, let me take that back, we use our standard deviation of the population, which is normally distributed with mean of 0 and standard deviation of 1. However, the other value, if we go ahead and replace with the sample standard deviation, would not have a mean of 0 and standard deviation of 1. Okay, so someone came along. It was a man by the name of William Gossett who worked for the Guinness Brewery. And he created a new model that accounts for the additional variability. He was in charge of the experiments for identifying the best barley for brewing and was using small data sets, which meant he did not know the population standard deviation. For various reasons, he couldn't publish under his name, so his results were published under the pseudonym Student, which is why this would be called the student t-test, not the Gossett t-test. It is not the version for students, it is just called student t-test. Okay, so suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t equal to x bar minus mu divided by standard deviation over the square root of n, it follows the student's t distribution with n minus 1 degrees of freedom, where x bar is the sample mean and s is the standard deviation. So small thing to say about degrees of freedom. Example, imagine you had 5 pens of different colors, right? So 1, 2, 3, 4, and 5 pens of different colors. And you had 4 students, or you had 5 students that wanted to borrow the pens, So let's say the first four, 1, 2, 3, 4, they borrowed all the pens. Now the last student, do they have a choice in which pen they're going to choose? The answer is no, they don't have a choice. So the first 4 students have some freedom as to which pen they could select from my little collection of pens, but the last student did not have any freedom. They're stuck with the last available pen. Okay, so let's go ahead and take, well, actually real quick. So for example 2 in the book on page 408, you can go ahead and look at comparing the standard normal distribution and the t-distribution using simulation with Minitab or StatCrunch. And if you have any questions on how that works, go ahead and please send me an email. Alright, so note, as the sample size of n increases, the distribution of t behaves more and more like the standard normal distribution. Okay, so let's go ahead and take a look at the properties of the t-distribution. So first off, the t-distribution is different for the different degrees of freedom that we're looking at. And remember, a lot of this is based upon the fact that we're using S for the sample population, the sample standard deviation, versus having the actual standard deviation from the population. Second, the t-distribution is centered at 0 and is symmetric about 0. And then the area under the curve is 1. This is good. This is something we've been working with before. And the area under the curve to the right of 0 is going to be equal to the area under the curve to the left of 0, which is 0.5 or half. So it's just, if you take 1, split it in half, you get half on one side, half on the other. I'll go ahead and draw an example. So if we have 0, the blue half is equal to the red half, which is both a half. And the total area, I'll go ahead and highlight in yellow, has an area of 1. Now, as t increases or decreases, without bound, so either heading off that direction or that direction without bound, the graph approaches but never equals 0. Okay, so it gets closer and closer to the horizontal axis bar, which I color in blue, but it will never actually touch it, even if you go to the left or the right. Alright, 5. The area in the tails of the t-distribution is greater than the area in the tails of the standard normal distribution because we are using S as an estimate of sigma. Because remember, S, we're talking about sample mean versus sigma, population mean. Thereby introducing further variability into the t-statistic. And as the sample size n increases, the value of S gets closer and closer to the value of sigma by the law of large numbers. So it's good as the sample size increases. So let's go ahead and determine the t-values. First off, recall, what does the notion z sub a mean? Well, it's used to represent the z-score whose area under the normal curve to the right of z alpha is a. So let me go ahead and write that out. Z sub alpha is used to represent the z-score whose area under the normal curve to the right of ZA is A. And remember, that's kind of odd because for our Z tables, we're given the area to the left. But when we're looking at this problem, it's technically talking about the area to the right. And that'll be something when we're looking at actually the t-tables. The t-table will give us the area to the right, which is different than the z-score or the z-tables. Alright, for example 3, determine the t-value such that the area under the t-distribution to the right of the t-value is 0.025 with 12 degrees of freedom. That is, find t sub 0.025 with 12 degrees of freedom. Be sure to draw a t-distribution curve and label the area as well as the t-value in question. Okay, so first off, let's go ahead and get a visual on what we're trying to find here. So we have our t-curve. centered at 0. Now we're looking for the t-value such that the area to the right of that t-value is 0.025. So we're trying to figure out what t-value has an area to the right of 0.025. The nice thing here, remember, in our table for the t-values, it gives us as the area to the right, which is different than the z-values. Let's go ahead. I've written down, or I've copied and pasted a small section of our table. This is found in the back of your book. And we're looking for, let's see, 12 degrees of freedom. So the column here with df, that's talking about our degrees of freedom. So we'll look for 12 right here. Go ahead and highlight that row. Next, we're looking for, let's see, t with 0.025. Aha! So it's going to be this column right here. And where do they intersect? They intersect at this value right here, 2.1719. So, how would we write our answer? Well, the area under the t distribution to the right of t equals 1.79 with 12 degrees of freedom is 0.025. So let's go ahead and write that. The area under the curve, or under the t distribution, let me go ahead and erase that, under the t distribution, so the area under the curve of the t distribution to the right of what? Well, we found out that we're looking at t equals 2.179 with, how many degrees of freedom are we looking at? With 12 degrees of freedom. Is 0.025, period. Okay, there we go. So this is one of the new things that's introduced with the t-table, remember, is we're looking at degrees of freedom. And we have to work with the degrees of freedom because we are working with the sample standard deviation and not the actual population standard deviation. All right, so here's a problem. If our degree of freedom is not listed in the table 6, sorry, that's table 7, use the next closest degree of freedom shown in the table. And usually we do this for degrees of freedom greater than 40. So you'll notice in your table 7 that you use all of the values up to 40, and after that it starts skipping values. So it goes from 40 to 60 and so on. So once you get there, anything higher than 40, just use the value closest to the degree of freedom that you are looking at. And remember, as our n value gets bigger and bigger, our sample size gets bigger and bigger, our sample standard deviation will start getting closer to our population standard deviation. Now let's go ahead and construct and interpret a confidence interval for a population mean. So constructing a 1 minus alpha times 100% confidence interval for mu. So provided, first off, the sample data should come from a random, so a simple random sample, or a randomized experiment. And then the sample size should be small relative to the population size, where we have n should be less than or equal to 0.05 times n. Once again, about 5% of your normal, or of your population size, sorry. And the data from a population that is normally distributed, or the sample size is large. Okay, so it's one, either you have a small sample size that's normally distributed, or the sample size is large. And then a 1 minus alpha times 100% confidence interval for mu is given by the following. So for the lower bound, we'll do x bar minus t alpha divided by 2 times s over the square root of n, and our upper bound would be x bar plus t alpha divided by 2 times s divided by square root of n, where t alpha divided by 2 is the critical value, with n minus 1 degrees of freedom. All right, and one thing to note, the margin of error for constructing confident intervals about a mean is going to be E equals T alpha divided by 2 times S divided by square root of n. Now let's take a look at example 4. So using the same data we had for example 1, we're going to construct a 90% confidence interval for the given data. So the first thing that we want to do is we're going to compute x bar and s, but we actually already found x bar previously. So I'm going to go ahead and write down our x bar from the other example, example 1. Okay, so that was 27.28, and then our sample standard deviation, you would go ahead and calculate this the normal way you would, which remember would be the square root of, we would have the sum of our xi values minus x bar squared divided by n minus 1. Okay, and then when we go ahead and use that, plug those into our calculators, we would get about 4.08. We'll go ahead and round it to that. Okay, so once we found our mean and our standard deviation, we're going to go ahead and determine the critical value, t of alpha divided by 2, with what degree of freedom? Well, n minus 1 degree of freedom. And you can go ahead and use df to abbreviate for degree of freedom. That's fine. Alright, so we're going to go ahead and do that. Let's see. Well, what is t of alpha divided by 2? First off, we need to find alpha. So let's go ahead and find alpha. To find alpha, we're going to go ahead and use a formula we're given, which is 1 minus alpha times 100. So 1 minus alpha times 100%, and we want a 90% confidence interval. So we'll go ahead and set this equal to 90%. I'll go ahead and change these from percentages into decimals, so that's going to be just 0.1. Sorry, not 0.1, that's just going to equal 1. So we'll go ahead and just write it as 1. Let me go ahead and actually re-erase this. So the 100% is just going to end up equaling 1 if we go ahead and write it as a decimal. So we get 1 minus alpha equals 0.9. Then, solving for alpha, we have 1 minus 0.9 equals alpha. And what is 1 minus 0.9? That's going to be 0.1. We have found our alpha value. So, then t of 0.1 divided by 2 is actually going to end up equaling t of 0.05. So now we're looking for the t value. Let me go ahead and draw a chart here. We're looking for the t value such that the area to the right will be what? It's going to be 0.05. And we're looking for how many degrees of freedom? Well, our degrees of freedom is going to equal n minus 1. And what is n? N is going to be our data values, which we had were 12. So 12 minus 1, which is going to equal 11. So that is our degree of freedom. We'll go ahead and look at our chart for the t values. Look for degree of freedom, 11, and then the area of 0.05. So when we do this, we find that, and let me find a nice spot to write this. Let's see. So t is going to equal, looking at column or row 11, column 0.05, we get 1.796. Alright, so we found our t value, 1.796. What are we going to do with that? Well, we're going to go ahead and use our formulas to find the upper and lower bound, which will give us the confidence interval. So our lower bound is going to be x minus t of alpha divided by 2, and our upper bound is going to be, our upper bound is going to be x bar plus t of alpha divided by 2 times s divided by n. So we go ahead and label these for the solving. So upper bound, or as usual for upper bound, I can go ahead and I'll say we can abbreviate it with UB. So upper bound, that is going to be x bar plus our t alpha divided by 2 times the s divided by the square root of n. Let me make sure I copied that down right. Awesome. And then our lower bound is going to equal x bar minus our t value. Let me erase that. Okay, so our t value, alpha divided by 2 times s divided by n. Okay, let's go ahead and plug in all the values we found. I'll go ahead and color code them. So x bar will be that. Let me go ahead and color code where they go into the equations. And n is 12. We get n from the amount of data values we are given. And then what color am I missing? Green. And my t value. Oh, I labeled that a little incorrectly. So our t value should be t of 0.05. Okay. That will be the t value. All right, let's go ahead and plug these in. All right, so I went ahead and I plugged in the values. Next thing we're going to do is plug these into our calculator and see what we get for the upper bound and the lower bound. Okay, so I went ahead and I plugged them into a calculator and I found the upper bound is about 29.4 and the lower bound is about, the upper bound is about 29.4 and the lower bound, I accidentally wrote UB, and the lower bound is about 25.16. So what does this all mean? What was all this for? Well, what we're saying is we are 90%, and notice we say 90 because we're looking at a 90% confidence interval. We are 90% confident that our mean is between 25.16 and 29.4. So these are that's the upper bound for our mean value, and this is the lower bound for our mean value. So lower bound and upper bound. And we're 90% confident because we were looking at a 90% confidence interval. All right. Now, number 5. Determine the sample size needed to estimate a population mean within a specified margin of error. So first off, what's the difference between rounding 7.42 up or rounding off 7.42? Well, if we were rounding up, we would go ahead and go to the next highest number, which would be 8. But rounding off, we would just go ahead and stick with 7. Okay, so rounding up and rounding off. And when we're looking at determining a sample size, we're going to go ahead and round up. So go to the next highest number, or the next number up. Now, determining the sample size n. The sample size required to estimate the population mean mu with a level of confidence 1 minus alpha times 100% within a specified margin of error, which you would denote with capital E, is given by the following formula. So n equals z alpha divided by 2 times standard deviation divided by E, our margin of error, squared. And where n is rounded up to the nearest whole number. Okay, so remember we're rounding up. Now let's take a look at example 5. How large a sample is required to estimate the mean within a 0.5 margin of error with a 90% confidence interval? We're going to use the standard deviation we found in example 4. So first off, what was the standard deviation we found in example 4? That was 27.28. Let me go ahead and still include my... Actually, let me fix that. It should be x bar, not x squiggle. So x bar was equal to 27.28. Okay, so we're going to go ahead and use our formula. So let's write that down. N is going to equal, we have, let's see, z of alpha divided by 2 times standard deviation divided by E squared. Actually, I wrote down the sample mean, but we need to use the standard deviation. Don't know why I wrote that out. We don't need this. We need standard deviation, which was, let's go back and check on that. Let's see, standard deviation was 4.08. Okay, so we have the standard deviation. Let's go ahead and color code that. Now, how do we find E? Well, we had the formula for the margin of error given previously. I'll go ahead and write down that formula. E is equal to T, alpha divided by 2 times our standard deviation divided by our sample size. So let's go ahead and find E first. So I'll go ahead and label that. Find E. And then we want the t-value of, and our alpha is going to be 0.5 divided by 2 times standard deviation is 4.08. And sample size was 12 because that's the data value we were using previously. So to find this, we need to find t of 0.5 divided by 2, which is going to be t of 0.025. And we're looking at a degree of freedom of 12 minus 1, which is going to be 11. So I'm going to say note degree of freedom equals 11. Put that in parentheses on the side so we don't get it confused. And then we'll go ahead and look in our chart. So let me go ahead. I'm going to flip to my chart. We're looking for degree of freedom is 11 and then 0.025. That'll be 2.201. And that was 201. Okay, so that is our t of 0.025. So plugging that in here, 2.201 times the 4.08 divided by the square root of 12. We'll use that to find our e-value. Let me go ahead and plug that in my calculator. And that comes out to about 2.6. So that is our margin of error. We'll go ahead and let me color code that. Okay, everything's color coded. I'll go ahead and plug these in. So we have the 2.201 times our S value, which is 4.08, divided by E, or margin of error, 2.6. We'll go ahead, square that. Let me plug that into my calculator and see what I get. And that looks like, when I plug it into my calculator, it comes out to about a repeating decimal, but about 214.14. And remember, we need to round up. So rounding up to the nearest whole number would be 215. So what does this mean? Well, a sample size of 215 results in what? An interval estimate of the population mean with a margin of error of 0.5 with a confidence interval of, let's see, what we're looking at, a 90% confidence interval. So 90% confidence interval of 90%. And there we go. Okay, once again, remember to round up to the nearest whole number. So here's a question that I am often asked by students. When do we know to use a t-score versus using a z-score? Well, generally, we use a t-score when we have a small sample size, which would be below 30. And also when we do not know the population standard deviation. So we use a z-score when we have a sample size greater than 30 and when we do know the population standard deviation. So here's a nice little visual flowchart that I've seen before. So the question is, do you know the population standard deviation? If the answer is yes, you would go ahead and look at this box. Then you're asked if the sample size is above 30. If it is above 30, you'll go ahead and use the z-score. However, let's say you do know the population standard deviation, but you don't know, but your sample size is not above 30. Then you would use a t-score. But you'd replace S with a standard deviation. So that's a small variation to this. And lastly, what we were just looking at is we don't know the population standard deviation, so we'd use the t-score. Okay? Alright, that's just a small flow chart. Hopefully that helped. And please email me if you have any questions with this section.